Okay, so today for the virtual problem solving session, there were 3 requests. The first was for homework 17, section 4.4, problem 3, so I'm going to do that first. And then the second 2 were for homework 16, problem 3, but different parts of it, so I'm going to work through that one next. So if you're here for that problem, go ahead and skip to like partway through the video. So for homework 17, problem 3, we're given the hint that we should be using the convolution theorem on this one, so I did pull up the formula sheet here so that we can go ahead and apply the convolution rule later. But we're trying to take the inverse Laplace transform of this quantity right here, 27 over s squared times s squared plus 9. And then I'm going to come over to the formula sheet real quick and kind of try to figure out like what parts we're going to need. We're given the hint that we should be doing the convolution rule. So that's that L of f star g is fg, as it's written on your formula sheet, or in the form we'll need it, L inverse of a product big F big G is going to be f star g, where we also need to use this definition of convolution right here, that f star g is the integral from 0 to t of f of tau, g of t minus tau, d tau. So our approach for this one is going to be to say, if I need to take the inverse Laplace of a product of two things, I can take the inverse Laplace of either separately and then apply convolution using this formula for the things that went into that product. So in order to do this, first we're going to have to define those products that are going to be most useful to us, and then just calculate this formula after we're done. So as far as defining this as two products, sort of the approach can be figuring out what parts of this would be doable by themselves. And so it's going to be to take s squared on one side, s squared plus 9 on the other, and multiply those two things. Normally, if you saw a funky product in the denominator, you might think partial fraction decomposition. This one's kind of hard because of the squareds there, and the convolution is going to be pretty straightforward. We do have to pick sort of how to break up the numerator, this 27, and the way we're going to do that is you could, like, absolutely foolproof, just put 27 out here and put 1 on top of each and then treat them separately. What I'm going to do though is leave behind the numbers that would be useful for taking my inverse Laplace of either part separately. So some number over s squared plus 9 is going to look for me like one of my inverse Laplace of this, taking me back to a cosine. Oh no, sorry, taking me back to a sine, this one up here. So I want the number on top to be like the number that's squared on bottom, so I would like a 3 there. Now this looks exactly like a sine Laplace transform. And then for my 1 over s squared, I know that s squared is going to look like this power rule right here. Let me just go ahead and write it down right now. L of t to the 1 is going to look like 1 factorial over s to the 1 plus 1, or 1 over s squared. And then I just did the same thing right here. And so I know that I just want a 1 in there to make it look like what comes out of the Laplace of t. And so that means that I'm going to leave on the outside 9. So I have 9 times 1 times 3 would give me that original 27. And so what I've written here is the exact same as what's up top, but I've broken it down into things that look like f and g. And I was thinking about it, whether I want to swap the order of those, but I think I'm okay with using them this way. So now I'm going to need to know how to get to little f and little g from each of these, but they are just going to be t and sine 3t, because I carefully picked the way that these two were written so that I could really easily copy them down from my basic Laplace transforms. So my inverse Laplace of the product big F equal to 1 over s squared and big G equal to 3 over s squared plus 9 is just going to be that 9 that I pulled out front times the convolution f star g. And for the specific functions that I got, it's going to be the function t star sine 3t. And then from here we can go ahead and just apply the convolution formula. So that's going to be integral from 0 to t of I want to plug in f of tau, g of t minus tau. So, f of tau I can just go ahead and plug in as tau. And then, I'm sorry, I can't make that thing go away. There it goes. And then g of t minus tau, I'm going to have to plug in t minus tau here. For my second function. So this is all that happened just now. So it's going to be 3t minus 3 tau, for example. And then to finish the problem, all I'm going to need to do is go ahead and evaluate this integral and then put in my answer in WebWork. Which I'm going to go ahead and move these things kind of over to the side. That way I can put my equal sign. For the evaluation. And I guess I'm going to have to do integration by parts here because I don't know how to integrate like t sine t, but I know that if I could get rid of that t by taking derivatives of it, I wouldn't be having a problem anymore. And then I think I even give you all on your formula sheet like those things, right? Yeah, right there. So if you needed this on the exam, you would have it. I don't always remember if it's supposed to be plus or minus, so I'm glad it's here. So you just have to pick what your u is going to be and what your v is going to be. And in this case, I want u to be the thing that goes away when you take derivatives, so I'm going to take u equal to tau. And then that means that my dv is going to be sine 3t minus 3 tau. Oops, I should have it down below. And my v is going to be the integral of that. My du is a little bit easier. It's just going to be d tau now. So I take derivative that way for my u, and then integrate. I just need to make sure I don't misplace any constants. When I integrate sine, it becomes negative cosine. But since I'm integrating with respect to tau and I have a minus 3 in front, I'm pretty sure I'm going to divide that by minus 3. So I think it's going to be just 1/3 cosine of 3t minus 3 tau. And I'm going to check that that's true just by taking a derivative. So derivative of cosine throws a negative. One-third swap to sine 3t minus 3 tau, and then I multiply out front by my minus 3, which is going to cancel those out. So yep, it looks like I did that integration properly. We'll go back there as a first guess if something goes wrong with the web work. But now I can go ahead and plug in my integration by parts formula, uv minus integral v du. So that's going to be u is tau, v is 1/3 cosine of 3t minus 3 tau. And I'm going to have to evaluate that on my bounds, 0 to t. And then I'm going to minus my integral of v du. My v is that 1/3 cosine of 3t minus 3 tau. And my du is just this d tau right here. And again, that still uses the same bounds from 0 to t. I'm going to move this over and hope I have enough room to integrate all on this page. Looks like I don't. So instead I'm just going to copy this over to the next. Okay. So for this first part here, when I plug in my upper bound t, I get t 1/3 cosine of 3t minus 3t, and then minus when I plug in 0, 0 times 1/3 cosine of 3t minus 0. And then I need to integrate 1/3 cosine 3t minus 3 tau again. So integrating cosine takes me to sine. Oops. And since I'm integrating with respect to tau, I again have to divide that negative 3, kind of same reasoning as I had when I integrated the sine. And that's going to be evaluated from 0 to t as well. So simplifying the part in brackets that we have to start, I've got t times 1/3 cosine 0 minus 0. So that's just going to go away. And then minus, when I plug in t here, I'm going to get 1 over minus 9 sine of 3t minus 3t minus 1 over minus 9 sine of 3t minus 0. I'm pretty sure cosine of 0 is 1. And then simplifying, I've got sine of 0 here. And then this minus minus turns into plus 1 over 9 sine of 3t I better check the sine cosine thing real quick. Yep, can confirm cosine of 0 is 1. That means sine of 0 is 0. And so this is just becoming t over 3 minus 1/9 sine of 3t. So let's check if that's right real quick. T over 3 minus sine of 3t over 9. It is not. Is it a pretty quick fix? Let's see. What could I have done wrong? Oh! I know what I did. I forgot the 9 right here that I had at the start and then just dropped it completely. So just imagine I wrote a 9 all over everything. There we go. So simplifying all that would actually become 3t minus sine of 3t. Ooh, I'm glad it was a pretty easy one to fix at the end there. So yeah, that's how this problem goes. I think that if you're getting it wrong, probably the integration by parts might have thrown you. Sometimes you all don't recognize when you should use integration by parts. Could be the same thing I just did where you dropped off that constant that you pulled out front. And also all these integrals of sine of 3t minus 3 tau or cosine of 3t minus 3 tau. I did want to go through that the slower way, just in case that throwing a divide by whatever's in front of the tau was confusing. So for example, if you're trying to integrate this thing, or same as when I was trying to integrate the sine, if it doesn't occur to you right away to look at the tau and divide by the thing in front of it, think of this like a u sub problem. So I would say u is 3t minus 3 tau, and du is negative 3 d tau. Or I can replace d tau with du over minus 3. So this becomes negative 1/3 integral. I am going to have to change those or go plug everything back in later. But that just becomes cosine of u du over minus 3. And I know that I can integrate cosine really easily. I have it here. Its integral is sine. So that just becomes minus 1 over 3 times another 1 over minus 3, pulling this thing out front. Integral cosine u du is just 1 over 9 sine u. And then I plug back in what u was, 3t minus 3 tau, and I can go ahead and evaluate it on the bounds from 0 to t. So if you think this integration here, you might get wrong if you do it in your head, just go ahead and do it the long ways with a u sub in the middle of your integration by parts. I know that makes it quite long. But also you can think about sines and cosines the same way as you think about exponents. Leave whatever's inside every time you integrate and just divide by the constant in front of the variable you care about when you take an integral, or multiply when you take a derivative. So hopefully that clears up the first problem that was requested. The next problem that was requested was homework 16, 4.3, problem 3. We're supposed to use Laplace transforms to solve this piecewise initial value problem. Okay, and it does that thing where there's a few different boxes where you have to put your answers. First, we're going to put Laplace of left in the first box, Laplace of right in the second box. Then we're going to isolate capital Y, put it in the third box, and then we're going to find the solution, little y of t, and put it in the last box. But to start taking Laplace transforms of both sides, first thing I'm going to need is to represent what's on the right side as something that fits on a single line of equation. So I'm going to sketch what I'm looking for here. I want this function to be 1 up until 3, and then I want it to be 0. And so on problem 2, which you all did before this, you would have practiced representing functions using the step function. Here I definitely know that I'm going to need to use like u of t minus 3 to cause a change here. And what I want is my function to default to being 1 before the u starts happening. I'm going to call this function f, I guess. So between 0 and 3 here, f is just 1. And then after 3, I want to cause something to happen. I want to change my function. And the way I want to change it is I just want to like make the 1 go away. So I'm going to do minus the function 1 starting at u of t minus 3, or just minus u of t minus 3. So this is like a function made up of 2 functions. This one is 1 always. This one is 0 up until 3, and then it's 1. So if you take this and then subtract this, you'll get this picture right here. And then in the lecture videos, I think I gave you all some like quick, easy formulas that you can go ahead and plug functions in if you need, which hopefully if this kind of visualization is hard for you, you can at least go by those rules. Yeah, oh, I guess sometimes if you all are doing this, there might be a temptation to do like u of t minus 0 here to make 1 start. But you never have to worry about things that start at 0 if your time is defined starting at 0, because the solution won't matter before that point. And it's just extra work for you to deal with. So I have seen that a bit, but you don't need to do that. If you do, it won't break anything. You'll have like e to 0 at the end and it just goes away, but it's extra work. So anyhow, my differential equation then is y double prime plus y, equal to 1 minus u of t minus 3. So I can go ahead and take Laplace of both sides to get started on solving this. So L of y double prime plus y is going to give me s squared capital Y minus s times y of 0. Oh, I guess I should write the formula. Minus 1 times y prime of 0. That's just my y double prime. And then plus capital Y for my just y here. I want to make sure I did that formula right. Oh, wrong place. Minus sy of 0 minus y prime of 0. Yep, so we're good. And then I go ahead and plug in my y of 0, y prime of 0. For me, they're both minus 2, so that just turns this into s squared y plus 2s plus 2 plus y. Or s squared plus 1 capital Y plus 2s plus 2. just grouping the terms that belong to y together, since eventually I'm going to have to solve for big Y. And then Laplace of my right side is L of 1 minus u of t minus 3. So L of 1 is just 1 over s, according to my sheet right here. And then L of u of t minus 3, I applied this property. My f, in this case, is just 1, and my a is 3. So a lot of the time when you apply this property, you need to make sure to transform it into looking like f of t minus a. In this case, f of t is 1, so f of t minus a is 1, so there's nothing special to do. And we can just directly plug in that this is e to the minus 3s times capital F, the Laplace transform of 1, but we just did that, we know that it's 1 over s. Okay, and then I'm going to go ahead and plug these in real quick to make sure that they're right before I try solving anything. Yep, okay, so the two sides of my equation are right, and now I just have to try and solve for y. So I've got s squared plus 1 big Y plus 2s plus 2 is equal to 1 over s minus e to the minus 3s 1 over s. Or big Y is equal to 1 over s minus e to the minus 3s 1 over s minus 2s minus 2, all of that over s squared plus 1. Yep, that looks right so far. So I'm going to write it on the next page, I think. So I've got 1 over s squared plus 1 minus e to the minus 3s 1 over s times s squared plus 1 minus 2s minus 2. All right, let's go ahead and make sure I solved for that right before we continue. Okay, I was really worried I was going to have to check all my formatting there, but looks like I got it in with all the parentheses closed in the right places, and this is what big Y is. So then our last step is just applying the inverse Laplace transform to solve for little y. And I'm just going to go ahead and start from left to right. Some of these take quite a while, so I'm going to do it term by term, and then I'll plug it all back in at the end. So if I'm trying to take L inverse of 1 over s times s squared plus 1, my options are to do a convolution or to do a partial fraction decomposition. I like partial fractions because then I don't have to integrate things, but we'll check the convolution afterwards and then see if it would have been easier, I guess. So what I want to do is I want to take 1 over s times s squared plus 1, and I want to make it be some constant a over s plus maybe bs plus c over s squared plus 1. And remember, I do like an s in the numerator here so that I have the option to balance out this s squared that's going to multiply by a, which means that I'm going to need to have 1 is equal to a times s squared plus 1 plus s times bs plus c. So that's as squared plus a plus bs squared plus cs. And we combine like terms. A plus b s squared plus cs plus a should be equal to 1. And 1 is the same as saying 0 times s squared plus 0 times s plus 1. So this becomes the system of 3 equations. 0 is equal to a plus b. 0 is equal to c. First I used those two on the s squared. Then I used those on the s. And 1 equal to a using this. So if a is 1, then I know that b has to be minus 1 from the first equation, and I already know c is 0. So this becomes 1 over s minus minus s over s squared plus 1. And then from here I can go ahead and apply linearity and then my standard Laplace transform properties. L inverse of 1 over s is just going to be 1 minus L inverse of s over s squared plus 1 is going to be cosine t. Right here, my k squared is 1, so it's just cosine of 1. I guess we'll go ahead and try also option 2. You also seldom post these requests. I really want to work out every possible way. We could also do this by convolution like we did for the first problem in this video. It's 1 over s times 1 over s squared plus 1. So this is my big F and this is my big G. And I know that I'm going to be applying this formula, integral from 0 to t, f of tau, g of t minus tau, eventually. And so I'm actually going to swap what I'm calling f and g. I'm going to call g this first one and f this second one. The reason I'm going to do that is because inverse Laplace of this is going to be 1. And just like we saw at some point, I remember saying it during this video, if f is 1, then f of tau is 1, and also g of t minus tau is 1. So you don't have to worry about the weird looking t minus tau if g is a constant. In that case, g equal 1 over s means that g of tau is just, I'll do this the long way, sorry. G is t, so g of tau is, oh sorry, g is 1, so g of tau is 1. And then f equal to 1 over s squared plus 1 means that little f is sine t. Sorry, that was g of t minus tau is 1, so f of tau is sine tau. So it's just going to be integral from 0 to t. F of tau is sine tau. g of t minus tau is 1, d tau. So I just have to integrate sine, which gives me minus cosine tau, evaluated from 0 to t. So I'm going to get minus cosine t minus cosine 0 minus cosine t plus 1, which is the same as we got from our partial fraction decomposition. So either approach is fine here. If you can integrate pretty easily, the convolution works. And if you're comfortable with partial fraction decomposition, that approach works. A lot of the time people seem to like applying convolution to every problem they meet once they know it, just because you can always plug in the formula and evaluate it. Okay. You can't have this ball right now. Sorry, my dog had a really noisy toy. So then let's continue with the rest of the terms. So next up we want to compute the second one. E to minus 3s 1 over s times s squared plus 1. But we got the sort of like hard part out of the way already. We can use either of these properties to know how to break up the 1 over s and the s squared plus 1 in this term, and then all we have to do is deal with the e using the step function property. I'm going to do the partial fraction one because it's my favorite. I'm going to make sure that I copied that down right. Yes. Okay. I like partial fraction too because then I can break this up into two different Laplace transforms. You could do the convolution as well. You would just have to remember to plug in the f of t minus a everywhere in the answer. But you would get the correct thing eventually. So in this case, I know that I'm introducing step functions because I had it in my initial problem, so usually it comes back in the inverse. And so L inverse of e to minus as big F is just going to be little f of t minus a, u of t minus a. So in both these cases, I've got a is 3. And then my f for the first one is going to be, oh, I keep going to the wrong place. L inverse of 1 over s is 1. And then my f for the second one is coming from s over s squared plus 1, just that cosine t again. So I'm going to get 1 u of t minus a minus cosine of t minus a u of t minus a. So that's just me taking my f of t minus a, u of t minus a, but my a in this case is 3. And remember, the function 1 is 1 at t and 1 at t minus 3, so you don't have to plug in anything there. It just stays as 1. Should be like uphill from here. The last two are a lot easier. So L inverse of 2s over s squared plus 1 is just 2 L inverse of s over s squared plus 1. That's just 2 sine t from, nope, did it a second ago and still got it wrong. It's cosine t from our table. And then L inverse of, I guess the last one must be 2 over s squared plus 1. Yep. Is just going to be 2 L inverse of 1 over s squared plus 1. Now I get to use that sign that I was pretty excited about, 2 sine t. And then from here, I just have to plug everything back in. So little y was L inverse of big Y. So it's going to be L inverse of this first part, which we said was just 1 minus cosine t. Minus the second part, which we did right here and got that. Minus the third and fourth functions that we solved here and here. So minus 2 cosine t minus 2 sine t. So that's going to be 1 minus 3 cosine t, just combining those two together, minus 2 sine t. I want to bring this with my other functions that don't depend on u. And then it's 1 minus cosine of t minus 3 times u of t minus 3. You could have also just plugged it in like this and WebWork would take it, but I wanted to simplify it to type a little bit less. And let's see if it came out right. 1 minus cosine of 3t minus 2 sine of t. Already I've started to type things wrong. Minus 3 cosine t is what I should be typing. Minus 2 sine t plus 1 minus cosine of t minus 3 times u of t minus 3. I hope it takes u. It didn't like that. Let's try capital U. It does not like that. Let's see what I could have done wrong. Oh, this whole thing was minus, and when I went to this right here, I accidentally made it a plus. That oversimplifying causing problems when it introduces new mistakes. But this is the correct answer now, since I transferred down my negative sign correctly now. And then that's how you finish the problem. I think that one warning, the web work that I got, the decomposition leads to like, I have s squared plus 1. That comes out of like here, having y double prime plus y. So if you have a different number right here, be careful because you're probably going to have sine or cosine of a different constant. And in that case, when you get to this step way over here of plugging in cosine of t minus 3, if you had like cosine 2t for your function, in this case that would become cosine of 2t minus 6. You have to do like 2 times t minus 3. So if you feel like you're doing this right but it's going wrong, check if that's your issue. Otherwise, it's really easy for just a little bit of algebra to catch you up here in the partial fraction decomposition, I think. Yeah, I think I think those are the two big places. Or when you're putting everything back together, like forgetting a minus sign or dropping off one of these easy terms because you get so caught up in the rest. There's just a lot of little places where mistakes can happen. So go back and check those if you're still getting it wrong. So that's everything that was requested. It took most of the problem solving session. I know that we've got some long, difficult problems these days, but good luck with your homework, and I will see you all in class.